Hi, I'm Akhil, and this is my AP Stats final project. Today I'll be exploring whether something as common as city noise might actually impact our health. Specifically, I'm asking whether there's a measurable link between how loud a city is and how often people in that city are hospitalized for cardiovascular disease. Cardiovascular disease, or CVD for short, is the leading cause of death not just in the US, but worldwide. At the same time, the World Health Organization has identified environmental noise as more than just a nuisance, but also a public health issue. Constant exposure to loud environments, especially in urban areas, can increase stress and blood pressure, which are both known risk factors for heart disease. So that led me to wonder if there's a statistical difference in CVD hospitalization rates between noisy cities versus quiet ones. That brings me to my first statistical question. Does the mean rate of CVD hospitalization rates differ between urban areas with high average daytime noise levels and those with low average noise levels? In my study, cities with noise levels above 80 decibels were considered noisy, while those below 75 decibels were considered quiet. So the goal here is to test whether there's a statistically significant difference in hospitalization rates between these two types of cities. To answer this question, I needed two types of data, noise levels and hospitalization rates. I based hospitalization rates on the CDC's National Hospital Discharge Survey, which tracks the number of people hospitalized for cardiovascular issues. For noise, I referred to historical data from the EPA's 1974 noise levels document, which gives estimated average daytime noise levels for different environments, which are still representative of today. The population I focused on was all urban areas in the US with either high or low average noise. From that population, I randomly selected 30 cities with average noise levels of 80 decibels or higher, and another 30 cities with levels below 75 decibels. Each data point in my sample represents the number of cardiovascular hospitalizations per 10,000 people in a city. Because the samples were random, independent, and approximately normal in distribution, I was able to use inference methods to analyze the data. Here you can see the table with some of the data that I used for this project, and you can also see a box plot on the right comparing the CVD hospitalization rates for noisy versus quiet cities. And right away you can notice that there is a higher median for noisy cities and an overall range of hospitalization rates that is larger than the quiet areas. And this visual difference shows that there might be a real statistical difference between the two groups. So I decided to move forward with a formal hypothesis test. To test for a difference in means between these two groups, I used a two-sample t-test for a difference in population means. So let's walk through Phantom's format for this inference test. The parameter of interest is the true difference in mean cardiovascular disease hospitalization rates per 10,000 people between noisy US urban areas and quiet ones. The null hypothesis is that the mean cardiovascular disease rates between the areas is equal, meaning that there is no difference in mean rates. The alternate hypothesis is that the mean rate of cardiovascular disease hospitalization rates in loud urban areas is greater than the quieter urban areas' mean rate. As you can see, all assumptions for inference are met. The samples were collected through simple random sampling. The observations are independent since one city's hospitalization rates don't affect the other, and the sample size is less than 10% of the population. And each group had 30 cities, which is enough for the essential limit theorem to apply and assume normality for the sampling distribution. The name of the procedure that was used is a two-sample t-test for difference in population means, and the test gave a t-statistic of 2.689 with approximately 57.8 degrees of freedom and a p-value of 0.0093. Since the p-value of 0.0093 is less than our significance level of 0.05, we reject the null. This means there is statistically significant evidence that the mean rate of cardiovascular hospitalization rates is higher in noisy US cities than in quieter ones. While this doesn't prove noise causes heart disease, it strongly suggests there is an association. And after testing whether a difference exists, my second question was how much higher is the mean rate of cardiovascular disease hospitalizations per 10,000 people in the US, urban areas with high average daytime noise levels, compared to cities with lower noise levels. So now I'm shifting from just asking is there a difference to how large is that difference. To estimate the size of the difference, I used a two-sample t-interval for the difference in means. This interval gives a range of plausible values for the true difference between noisy and quiet cities. The parameter is the true difference in mean CVD hospitalization rates per 10,000 people between noisy and quiet urban areas in the US. As you can see, all the conditions were satisfied. The cities were randomly selected. Each city's data point is independent of the other, and the sample size is less than 10% of the population. And because we have 30 observations in each group, the central limit theorem allows us to assume normality of the sampling distribution. The name of the procedure used is a two-sample t-interval for the difference in means, population means. Using a t-critical value of approximately 2.002 and degrees of freedom of around 57.8, I calculated a margin of error of 7.69. This gave me a 95% confidence interval of 2.64 to 18.02. So we can conclude with 95% confidence that the noisy urban areas have between 2.64 and 18.02 more hospitalizations per 10,000 people than quiet urban areas. Because this interval doesn't include 0, we have strong evidence that a real difference exists. If the interval had included 0, we wouldn't be able to say that the noise level and hospitalization rates are associated. To summarize, both the hypothesis test and confidence intervals show strong statistical evidence of a difference. Noisy urban areas tend to have significantly higher cardiovascular hospitalization rates compared to the quieter ones. The interval supports that the difference isn't just by chance, and it may be meaningful enough to raise public health concerns. This doesn't prove that noise causes heart disease, but it does suggest that noise pollution is an environmental factor worth paying attention to, especially in urban planning and public health decisions. As a reflection of the study, one thing that went well was defining clear comparison groups such as noisy versus quiet urban areas, which made my statistical analysis easier to organize and present. The box plot gave me an early visual cue that there might be a difference, and also using the right inference methods also showed I understood statistical concepts. What didn't go as smoothly as I would have hoped was finding real data that combined both noise levels and health outcomes by city. But of course, I ended up finding it in the end. It's just that that part of the project took me a while to complete. If I were to continue this project, I'd include other variables that could affect hospitalization rates like income, access to healthcare, population density, or air quality. Using multiple regression could help control for these confounding variables, and it would also be interesting to see if this pattern holds in suburban or rural areas. Looking at data over a longer time period could show whether long-term noise exposure has an even greater effect. Also, comparing cities across countries with different noise regulations could also lead to some meaningful public policy insights. These are the sources I used to support my project. They include the CDC for heart disease data, the World Health Organization for noise-related health risks, and the EPA for historical noise level data. All of them help me model realistic data and ground my findings in real-world concerns. Thank you for listening.